Welcome to 57th lecture in the course of Industrial Engineering and Operations Research. Today we will start probabilistic inventory models. Because demand is uncertain, reorder point is uncertain, there are many uncertainties which can be tackled by means of the probability theory considering randomness. But to begin with, I will just solve one deterministic problem for your practice. An industry requires 4000 kilogram of raw material for manufacturing an item per year. Okay. Some item means many quantities of that item. So, you require a raw material of rupees 4000. Okay. So, this is 4000 kg. 4000 kg is needed. Cost of placing an order is rupees 35. So, ordering cost is rupees 35 per order, and the cost of carrying inventory is 20% of the investment in the inventories. So, this is 20% of the investment. The price is rupees 12 per kg. So, price is rupees 12 per kg. Determine optimal lot size, optimal order cycle time, minimum inventory variable cost. That means it includes holding and setup cost, but not the fixed purchase cost. That's why it is called inventory variable cost. Basically, inventory cost which you have been telling that till now. Solution is that given annual demand D is equal to 4000 kg per year, ordering cost C0 is rupees 35 per order, and then holding cost CH is equal to 25% of the price per unit of raw material. So, per unit is costing priced at rupees 12, its 20% is 0.2. So, this becomes rupees 2.4 kilogram per year. Now, you have got the data by economic order quantity model. You get Q star is equal to under root 2DC0 divided by CH. So, put the values 2 into 4000, C0 means ordering cost, that is 35, CH means holding cost per unit in that period, that is 2.4 only. So, if you do that, you are getting quantity as 341.56 kg per order. That is the answer about optimal lot size. Now, optimal order cycle time is T star is equal to Q star by D. Okay. Annual demand is 4000 kg, but you are ordering 341.56 kg in one order. So, that means 341.56 divided by 4000, that means 0.085 year. That is the optimal order cycle time. You can multiply it by 12, you will get the answer in months. If you multiply by 365, you can get the answer in days. And then the another question was that per year minimum total inventory variable cost, that is given already under root 2 D C0 CH. So, 2 into 4000 into 35 into 2.4, that means it is basically 819.756 per year, but this is rupees. Okay. So, this is rupees. So, that is the answer about this problem. Okay. Now, let us discuss probabilistic EOQ model. Probabilistic economic order quantity model is an extension of the classical economic order quantity model that incorporates uncertainty in demand during the lead time. Okay. It incorporates uncertainty in demand during the lead time. Lead time means that suppose you order some quantity, but it will not come immediately, it will take some days, maybe it will take 10 days. During 10 days, if you have already some stock, but it may be insufficient. Okay. It may be insufficient and you may get shortage. So, we are more concerned during the lead time of the event, okay, where we start ordering, because something that because we naturally order that when some quantity is left, okay, that time we order, So there is no chance of shortage before the lead time, but after before the reorder time. But during the lead time, that means during the point when we order and the point when we get, that difference, that lead time, you may get shortage type of situation, which may cause harm to company, okay, because it may cause customers may be highly dissatisfied and you may lose valuable orders. So this we have to see that this point, that uncertainty will be considered mostly in the lead time. The classical EOQ model assumes deterministic and constant demand. However, the probabilistic version accounts for the random or variable nature of demand, which is more realistic in many practical scenarios. So demand is basically random, and the critical period during inventory cycle occurs between placing and receiving orders. In this period, shortage of stock may occur. So this is the point has to be paid attention, that basically critical period is basically between placing and receiving the order. Hence, a buffer stock has to be maintained to take into account uncertainties. So now let us see that this figure shows the relation between the buffer stock, or which is also called safety stock denoted by B, and the parameters of deterministic EOQ model, that includes Q, that means Q quantities have been ordered, lead time L, and average demand mu L during lead time. So what I am doing here, that suppose this is buffer stock, this has to be maintained over all time, and let us say Q quantity is inventory level, can be Q. So when you order Q quantity, then inventory level becomes B plus Q, and on an average at lead time is basically this one L. So this is the lead time, that here I place the order and here it is this one, and average demand mu L during lead time is mu L. So that means we have to keep that mu L plus B, okay. So B plus mu L, that thing has to be kept, and these are the usage rate. So assumption is that we demand each per unit time is normal with mean D. So we do not take deterministic D now, it is normal distribution. We say mean is D and standard deviation is sigma, that is we denote it by N D sigma. N means normal distribution, D means mean, and sigma is that standard deviation. Under this assumption, the demand during lead time L should be normal with mean mu L is equal to DL. So this is total, if we say that this is the demand per unit time is D, okay. So if we say that per unit time demand is D, then naturally that lead period is L. So the demand will be, average demand will be mu L is equal to D times L, and standard deviation will be sigma L is equal to under root L sigma square, because variances get added up. That is why it will be this one, but this adding up the variances etc. is for integer value. So here we are assuming that L is an integer value, that is the assumption, okay. Suppose we can say per day wise, so day means these many days, so that means average. The size of the buffer B is determined such that the probability of shortage during L is at most alpha, okay. So we can say that of course shortage, you can, even if you keep so many quantities, you can never guarantee that there will not be shortage, but that probability should be small. So we say let XL be the demand during lead time L. Suppose actual demand is XL, then it should be probability that this demand is more than buffer plus mu L, greater than buffer stock plus mu L. This is, it should be smaller than alpha, where alpha is a small number. Now we can of course normalize the normal distribution. We can keep the mean at 0 and standard deviation is 1. In that form we can express, and we can say N0 1, and Z can be written as Z is equal to XL minus mu L by sigma L. So we do the transformation of variables and we use Z parameter. So in terms of the Z parameter now, P is equal to greater than XL than this thing. If I put that thing in terms of this one, then this becomes naturally Z greater than B sigma by L. Okay, that is just it is simple transformation, because XL should be greater than, I already said that XL should be greater or equal to B plus mu L. Okay, that is what it was written. And if I say that XL minus mu L, therefore this should be greater or equal to B, and it follows that I just transformed it here. And if I say that XL, if I divide it by sigma L, I can divide it by sigma L. This is positive quantity only. So this quantity can be put at Z, and therefore Z is greater or equal to B by sigma L. So therefore Z is greater or equal to B by sigma L, and this probability is smaller than alpha. So this one normalized distribution has been plotted here. Suppose this is 0 line and this is Fz and this is N01, and this probability is alpha. Okay, maybe some value of K alpha in terms of that Z, and this is called, this is the risk of stock out. That means this much probability is there that stock out is there. So standard normal distribution should be like that, probability of Z greater or equal to K alpha should be smaller than alpha. Okay, so that means this is equal to this one. Now what happens, that it follows that B should be greater or equal to sigma L into K alpha. Okay, so this is this thing, B should be greater or equal to sigma L. So this amount provides the minimum value of buffer, that is the buffer stock. Okay, so that means you can see that buffer stock has to be more if sigma L is more, and also if this one is, this point is shifted, that means K alpha is more. Okay, let us understand it through an example. Question: the EOQ of a product is 1000 units. Assume that the daily demand is in 1010, that is D is equal to 110. Okay, economic order quantity of a product is 1000 units, daily demand is 100 with standard deviation 10, that means 100 units per day, and standard deviation sigma is equal to 10 units. Determine the buffer size B using alpha is equal to 0.05, something like 95% confidence level. Okay, so alpha we have taken, that means probability that you get stocked out is something less than 5%. So effective lead time L is 4 days, that is also given. So if that thing has been given, then we can find out sigma L is equal to under root sigma square L. That means 10 is the standard deviation, 10 square into 4, so it becomes 20 units. So therefore in the lead time that you get, standard deviation is equal to 20 units. Now from standard normal table, the value of K 0.05 is 1.645. You already knew that between plus minus sigma, that you know that 1.64 was between sigma 1.645, so much data lies. Okay, so this value is obtained from the Z table. Okay, so that means this will be, if you suppose this is a 0 line, and if it was a normal distribution like this should have been Z, and this is suppose that value is Fz, and suppose this value was this is the peak here at 0. In that case, between this is what, if I put that 1.645 value, okay, standard deviation may be 1, or I should say, if I plot in normal way, that means 1.64 times standard deviation. So more or less this area will be only 5%, okay, of the total area. So that's why standard normal table gives you value of K 0.05 is 1.64. Therefore buffer size is simply computed as buffer size is equal to sigma L into K alpha, that means B should be greater than 20 into 1.645, that means 33 units. So that means 33 units should be kept extra to account for the uncertainty. Okay, that is what that it has be to be given, other than your normal this thing, because that means this much times 1.645 times the standard deviation. Okay, let us now discuss the further more complicated models. Okay, here because the previous model is just based on EOQ model, but we are just introducing probability afterward, but here we are doing somewhat different way. So figure depicts a typical change in inventory level with time. Shortage may or may not occur during possible random lead times. Okay, so lead times are also random. Okay, because it is random lead time. Here this is lead time is different, here lead time may be different. Okay, and policy calls for ordering the quantity Y when the amount of inventory on hand drops to level R. So as soon as your quantity becomes R, you make a rule, then you order quantity Y. Okay, like here quantity became R, immediately I ordered the quantity Y, and but it came after some lead time, meantime some consumption was done, and you suddenly it became jumped by Y. But fine, there is no shortage here, but then here it was already there was some shortage, and then you got Y quantity, and here also it happened like that. In the deterministic case, the reorder level R is a function of the lead time between placing and receiving an order. You decide the reorder level based on how much is the difference between placing and receiving an order. The optimal values of Y and R are determined by minimizing the expected sum of setup, holding and shortage cost per unit time. But here we will find out that what is the optimum value of Y and R. Okay, what should I make the policy? So model is based on the three assumptions. Unfilled demand during lead time is backlogged. Okay, unfilled demand during lead time is backlogged, that means we have to fulfill that order. No more than one outstanding order is allowed. The distribution of demand during lead times remains stationary with time. So this I am following from the Taha's book. Okay, so notations are taken from that H.A. Taha book of operations research. Now just see, to develop the total cost function per unit time, let Fx is equal to PDF of demand during lead time. So Fx is the probability density function during lead time. Okay, that means Fx into time, x is units of item. Okay, that means it is how much unit of that. So this is this one. So D is the expected demand per unit time, H is the holding cost per inventory unit per time, P is the shortage cost per inventory per unit. That means shortage cost, if you are not able to give the order, maybe you are losing the profit, that you can consider as the shortage, or you can add some penalty because the customer will be annoyed also. So like that you fix up some shortage cost, and K is the setup cost per order. So if this much is there, then figure depicts a typical change in inventory. Okay, fine. Now here the element of the cost function are now determined. So setup cost is the approximate number of orders per unit time is D by Y, because D is the demand divided by Y. So in that type of, in that unit time, the demand was D, and so approximate, and Y is the thing at one time you get Y amount. So D by Y is this one number of order, so that the setup cost per unit time is approximately KD into Y. So you simply say KD into Y. And expected holding cost is that, because holding cost why expected, because there is a randomness. Okay, how much demand will be there, depending on that it comes. So, therefore, there is a huge amount of randomness. So, given I is the average inventory level, the expected holding cost per unit time is H into I. If I can find out the inventory level, then I can multiply it by holding cost in per unit. So, it will be HI. The average inventory level is computed as I is equal to Y plus E R minus X, okay, plus E R minus X by 2. So, that means this formula averages the starting and ending expected inventories in a cycle. So, it is somewhat approximation. We say in the beginning we have Y, because Y amount comes, plus ER minus X, that means there may be some backlog, etc. So, that is why plus ER minus X, and here it will be at the end that this is ER minus X, okay. R is the reorder point and divided by 2. So, it becomes Y by 2 plus R, because ER minus X can be written as E of R minus E of X, and this is constant only. E expected value of R is R only, and this is basically X. So, you put that R minus X as an approximation. The expression ignores the case where R minus Ex may be negative. So, it is assumed that R minus Ex is positive only. Now, expected shortage cost. Shortage occurs when X is greater than R, that means your value demand is more. So, it is expected value per cycle is computed. So, expected value per cycle will be R, that means reorder point, that quantity was there, and then it is R to infinity, that means demand can be, if demand is more than R, only then you will get shortage, because R is there with you buffer, and this becomes a R, because in during lead time you already have R quantity. So, that means if the demand is less than R, no question of any shortage. So, shortage will occur if X is more than R. So, that is why it is going from R to infinity. So, R to infinity, because infinity means demand in the lead time can be infinite also, theoretically. It is just concept, because it may not be infinity, but we are mathematically we are doing R to infinity X minus R, and Fx is that probability and dx, okay, because Fx is the probability density function. So, this is X minus R into Fx dx. So, Fx dx becomes the probability together. So, probability multiplied by the variable gives you the expected quantity. So, this is how that it goes, because P is assumed to be proportional to the shortage quantity only. The expected shortage cost per cycle is Ps. So, this is Ps, and based on dy cycles per unit time, then the shortage cost per unit time is P dsy, because I have multiplied Ps and then number of cycles P dsy. The resulting total cost function per unit time is now TCYR dk by y, okay, because dk by y was kd by y, rather kd by y, dk by y same, plus h into this much quantity holding cost, and this is the expected shortage cost. So, all the costs have been added P dy. So, now you see that this function contains the total cost is dependent on y and r. So, therefore, it can be minimized, and it is a function of two variables. So, what is the procedure? That I partial derivative with respect to y should be 0, and partial derivative with respect to r should also be 0. So, optimal values are determined by del Tc by del y. So, this becomes what? If you differentiate dk by y with respect to y, you get minus dk by y square. Plus you differentiate this quantity with respect to y, this will not come into picture, because it is not a function of y, but other part only h by 2. So, you get h by 2. Similarly, here minus p ds by this one, because you differentiate with respect to y, only minus p d by y, s y square will come. Okay. S means entire that thing has been written S just for briefly. Similarly, if you do del Tc by del R, this becomes h minus Pd by y r to infinity fx dx. Now you have to differentiate with respect to r. So if you differentiate, first portion will give 0, this will give h because you differentiated with respect to r, and this will give minus r, so minus fx type of thing. So this becomes minus p dy and this is the thing. So these two equations are there, and they will yield you that if you simplify that from first equation, you get this thing, okay, y star is equal to under root 2d k plus ps by h, and from the second equation also you get like this. So these are the two equations and two unknown. That means my r is unknown. Where r has gone? R is in s, basically s was x minus r fx dx. So r is hidden here. So basically you can say r is unknown and y is also unknown, but you have got two equations. So this can be solved by any numerical method way. Any numerical method can be done. So optimal values of cannot be determined in closed form, but the algorithm converges in a finite number of iterations provided a feasible solution exists that we can do that. So for r is equal to 0, previous two equations yield this one. Suppose we first take r is equal to 0, and it is also can be shown if the unique optimal values of y and r exist if this quantity is more than this quantity. Okay, this is just, it can be mathematically derived, but I am not going into detail of that. Smallest value of y star is of course under root 2k d by h. It occurs when the shortage is 0. So that is this one, and then you keep doing that. So steps of the algorithm will be that step 1 will be that you have to use the initial solution y1 is equal to y star, and this will be under root 2 k d by h, and let, so in the beginning let r0 is equal to 0. That means you have taken buffer stock to be 0. So you have in the beginning it will be 0. So you have taken 0, and then after that what you will be doing that, and set I is equal to 1 and go to step I. Okay, next step, okay, use yi to determine ri, okay, and if ri becomes equal to ri minus 1 in two consecutive iterations, then you can stop. Optimal solution, this becomes y star is equal to y and r star is equal to this one. Otherwise use ri to compute yi and set I is equal to I plus 1 and repeat step I. This can be written as step I basically, yeah, you can say step 2 instead of step 2 it will become, it keeps rotating and you keep doing that type of thing. So this type of procedure will be there, okay, that means you can keep doing that. Otherwise there is another way of that solving these two equations. Suppose you have these two equations, I can say that, suppose I write this equation as y star minus under root 2d k plus ps by h whole square, okay, plus, and this is again you say that bracket close, and this is r star infinity, this is fx dx, and minus hy star by pd, and again we say whole square. That means I have taken left hand side minus right hand side and a whole square and this thing. So this becomes one function, it becomes error function. So it is a function of two variables y star and r star. So I can use any optimization algorithm, there are many optimization algorithms to find out the value of y and r, okay. So one way is that you just find out value of y from one equation, substitute in the other equation, and then you get the value from the other case, another variable, and put in this one. That is one way. Otherwise you can use any optimization procedure, and there are many things. So I am not telling that any particular thing, but you know that Taha had explained in that way that you know that you do 1 by 1. Okay. So, that means you obtain some variable from one equation, understanding that the second variable is fixed, then you put that value in the second equation and then you obtain the other value. So, like that it can go this way also. Okay. So, that means this is done in a iterative manner. Okay. So, this is what that we can do that, and we will solve one numerical example also, but that we will be solving in the next class. Okay. That means this one. So, basically today we have talked two methods about the probability. One was very simple approach, that means based on the deterministic, but we just are trying to find out the buffer stock. In the second one, we are trying to decide that what value of R and Y should be taken so that it should be optimal. Okay. So, thank you very much for your attention, and this is okay.